So thank you, Taylor. Up next, our first presenter for the day really is, from an organization that's made a lot of news this week. They, as Taylor said, they're from CERN. Tim is from CERN. Yesterday, CERN started the Large Hadron Collider again for the first time in a couple of years, and they doubled the energy. They're searching and trying to unlock the secrets of the universe. And in the process of doing that, the collider itself generates a huge amount of data. Tim will tell you more about that. And to solve this challenge of analyzing all that data, CERN and Rackspace have worked together on Managed Cloud and OpenStack. And here's a little video about what's going on at CERN.
I'm Tim Bell, Infrastructure Manager at CERN, the European Laboratory of Particle Physics. CERN is trying to solve the mysteries of the universe, trying to understand how the universe fits together, the fundamental building blocks, and how those building blocks behave. At CERN, we have the largest piece of scientific equipment on the Earth. This is the Large Hadron Collider, a 27-kilometer ring 100 meters underground. We use that to collide beams of particles and then study the results. This produces about 1 petabyte a second. At one of the OpenStack summits, CERN and Rackspace discussed items around deploying large OpenStack clouds. We both have experience of this and found we had a number of things in common. The work with Rackspace has been particularly interesting because as we look out towards the growth of the compute needs for physicists, we can see that as we collide the beams with a higher and higher energy, that the compute needs are requiring to increase also. Testing environments such as Rackspace Public Cloud allows us to be confident that we have the possibility to expand out to public cloud resources as the needs of the physicists increase.
Ladies and gentlemen, please welcome Tim Bell from CERN.
Thanks, John.
Thanks for the introduction, John. CERN as part of the migration towards a cloud-based environment for research. CERN is the European Laboratory of Particle Physics. We were founded 60 years ago as a place where scientists could work together in peace in order to understand the fundamental nature of the universe, how the universe works, what it's made of. As part of that, we have built up a facility which houses around 11,000 visiting scientists, and that provides the basis under which they can do their experiments. While doing this research, we've also had a number of spin-offs. The aim of CERN is not to be actually producing spin-offs directly. However, a number of things comes along. If you can imagine a world without the World Wide Web, without the capacitive touchscreen, without the MRI scanners in hospitals, it will be a very different world, and this has come as a direct offshoot of the fundamental research that we're doing. The organization's funded to about 1 billion Swiss francs a year, so it's the cost of about a cappuccino per person in one of the 21 member states. For the last 2 years, we've been aim behind that is to allow us to then be running at the higher energy, and as was mentioned, we had the great result yesterday that the accelerator is now starting up again and colliding at twice the energy that allowed us to collect the Nobel Prize for the Higgs boson discovery in 2012. If you ever get a chance to go underground, this is 100 meters underground. It's a 27-kilometer ring. The magnets themselves, there are 1,200 of them, are cooled down to minus 271 degrees centigrade, so they become superconducting. Inside there is two small pipes about 1 centimeter across. We fire protons round at 20 kilometers a second below the speed of light, and with that we're then able to simulate the conditions just after the Big Bang. To see what's going on, we have detectors. These are basically digital cameras. They take pictures of the collisions. The difference between this and your Instamatic is that these are about 100 megapixel cameras, and they take 40 million pictures a second. They're also 7,000 tons and about the height of Westminster Cathedral. What do they produce? A petabyte a second and some great pictures. So these are some collisions from the previous run. Now, if you can imagine, the physicists have to go through millions, billions of collisions to try and find what they're looking for. It's been compared to looking for a needle in a haystack when you don't even know what a needle looks like. So how do we do this? CERN on its own cannot do this. So we are the center that records the data, the tier 0, but we have 170 other organizations around the world that collaborate with us in the worldwide computing grid. Here we run 2 million jobs a day in order to analyze this data and also to simulate what the theory should be telling us should be happening. So currently, we finished run 1. That was about 2 years ago. We spent 2 years doing the upgrade to then get the energy of run 2. So during run 1, we were getting between about 15 and about 27 petabytes a year, which we recorded. Run 2, double the energy, E equals mc squared, we expect to see coming on towards double the same amount of data. Looking forward with the program we have for physics, 2018 we'll do another upgrade, and then 2023 another one. Result, we're probably looking at 400 petabytes a year during 2023. This means that we have significant need for compute in order to be able to analyze all of that data. The CERN environment, based in Geneva, has a nice data center. Built in the 1970s, it used to have a cray in one corner, a mainframe in the other. Nowadays, it's packed full of industry standard servers, or when I say packed, it would be packed a lot more, except that we are limited by cooling and electrical capacity on site. The accelerator takes 120 megawatts, and they let us have 3 megawatts for the computing. So clearly, looking at run 2, we had to find a way under which we could expand and become more dynamic, to be more able to adjust to the working environments of the physicists. One of the constraints that we have is that we follow a public procurement model. CERN, as a government-funded organization, has to be sure to distribute the work and the orders across the member states of Europe. And so as part of that, we go through a very formal process of user acceptance, specifications, market surveys, burn-in, and then the hardware is eventually delivered to our users, of the order of 280 days after the initial idea was conceived. This isn't very agile. So what do we look to do in order to meet the needs for run 2? The first step was to increase our computing capacity. We asked our member states to make us proposals for data centers and chose one in the Vigna data center in Budapest. It's linked up with a couple of 100 gigabit links so that we can run this as a seamless facility. And with this, we're able to double the computing capacity that we make available in run 2. However, doubling the computing capacity would not mean that we should then double the number of staff. So what we had to do at this point was to look at how we were managing our systems and look at how can we optimize that. So what we chose to do is, rather than inventing things that were CERN specific, we looked out. We looked at the big hosting companies, the Web 2.0 organizations, and we then adopted their processes and their tools rather than inventing our own. One of these we chose was OpenStack. So the current status of OpenStack at CERN is we have the largest cloud is about 5,000 servers across the 2 data centers. We actually have 3 other clouds. Underground, right next door to the detectors, there are large farms that filter data from the accelerator. Those were idle for the last 2 years, so they spun up OpenStack on them and have been using those as facilities for simulation. And then during the run, when the accelerator is having maintenance work done, they'll spin up OpenStack again. All of the work that we do is done in the open. It's a very strong CERN tradition of contributing to open source communities. And therefore, where we have the code, we submit it upstream to communities such as OpenStack. Even where there are things we don't think other people want, we make it available in case anyone wants to browse. One thing to consider as you're reflecting in terms of how to transit is the model of the OpenStack package. So some people look at OpenStack and think that it's a CD you can put in your machine and then run. In fact, OpenStack gives you a core, a framework around which you can build your cloud service. And it's really important to consider the aspects outside of the pure API implementation as part of the work you do. There's all the work to package it, to integrate into your environment, your security systems, how you arrange to burn in large amounts of hardware when they arrive, the service levels that you expect to get. How are you going to monitor this and integrate it into your environment so that when things go wrong, your system administrators get informed? So it requires a lot more circles than just the basic code that you can download. And particularly, it's therefore well worthwhile as you do this to reflect in terms of the skills profile you have in your organization if you're looking to deploy OpenStack. and make sure you choose the right point. You can build your own, but you do need to have a skilled team to do it with. You can use distributions, Rackspace Private Cloud being one, to then deploy that using the benefits of the knowledge that come with that distribution. You need good Linux skills in that case. Or you can go towards a public or a managed offering from one of the public cloud providers. What's great is following the recent OpenStack summit, there is now a brand. The OpenStack-powered brand shows that the cloud to which it is concerned has passed a compatibility test suite. That means if you're talking to one OpenStack cloud, which is OpenStack-powered, and you then talk to a different one, you should expect the same behavior. At the same time as we're doing this technical transformation, we're also doing a major organizational change. For those of you that remember secondary school physics, Hooke's law involves springs. So you apply a force to a spring, and if you apply enough force to it, it deforms. What we concentrate a lot in terms of these transitions is the speed at which the front part of the organization is moving. It goes rapidly ahead, adopting continuous integration, agile methodology, DevOps. But it's really important to also consider the other parts of the organization which may be not moving at the same speed. Combinations of skills, combinations of application. And in particular, avoid the scenario of deformation that can come from one side going very fast and the other side not keeping up. So how do we handle this? We formed a small team. It was of the order of 9. And it was a combination of older, more experienced people who've been working with the systems, and also new hires who had some knowledge in these tools that have been used. And with this combination, we then went through the deployment process. As part of this, we encountered a number of interesting cultural scenarios. These really are extended examples. CERN doesn't have these, but just to give you a flavor of the kind of things that we encountered. So there were the people that felt we were being too hasty, that we should take our time. We only had 2 years to do this in. We couldn't hang around. There were the budget holders who previously had budget to buy hardware, and now what they were doing is they were giving quota on the cloud and service level agreements rather than the ability to talk directly to the hardware vendors. We had the experts who were confronted with a skills inversion where people were coming from college with knowledge about the tools, and they hadn't yet got that same level of knowledge. And then finally, the precious services, those ones that you really need to be careful when you make that choice to move to the cloud. So there will be some scenarios where it doesn't make sense to move the workload to the cloud. And you need to analyze those and avoid people in their enthusiasm move too much. So one of the other aspects that helped us greatly as part of the transition was working through with OpenStack. There's a summit every 6 months. And during one of these, we had a large deployments discussion. The big OpenStack cloud people sat down and talked about what was good, what was not so good. And Rackspace and CERN found a number of things we had in common. So through the CERN Open Lab, which is an industry collaboration partnership, the aim being that we take the extreme computing conditions of the LHC and then use those to drive research with industry such that when CERN needs a solution, it is available and tested. And then equally, when industry needs that afterwards, it's already had that validation that says, if this works at CERN, chances are it will work in your organization. On top of that, it's an open organization. We disseminate our results, and we also train people. So people come to CERN, spend a number of years on this, and then return to their home countries as part of that knowledge transfer. We're now in our 5th phase. Each phase is 3 years. And Rackspace was in phase 4 and have now recently extended their agreement into phase 5. In addition, one of the things that's different in phase 5 is we have some additional laboratories involved. So this is the biology lab from Cambridge and the GSI Darmstadt nuclear research lab. So we can take multiple use cases and apply those with these companies. So where was CERN and Rackspace finding things in common? So we had a private cloud we knew was going to grow. We had the Rackspace public cloud that we knew we wanted to be starting to look at interactions with. At the same time, we had these massive trigger farms, 100 meters underground, that we knew were arriving, and large numbers of small clouds appearing in our collaborating institutes. Now, for the average physicist, to handle the complexity of all of these different clouds would be a problem. So wouldn't it be great if we could find a way under which the physicists could think they're dealing with a single resource? So at the start of the work, we developed OpenStack Identity Federation with Rackspace and other members of the OpenStack community. What this allows you to do is to take a CERN user, log in through Active Directory at CERN, and then after that, use a remote public cloud resources within the trust and policy agreements that are set. In addition to that, we validated the CERN simulation workloads, the CPU-intensive workloads, on Rackspace private and public clouds. And they got similar results in reliability and performance to the ones we were seeing in the private cloud. So therefore, we knew that we were in a position, if in future we needed to, we could be using these resources. Going on, for this year, we've set ourselves the goal of being able to share images. So you should be able to easily take an image from one cloud, use it in another one, and in particular, be able to look at multi-cloud orchestration. I want my database on-premise. I want my web services in the public cloud. Instantiate me that application. At the same time, we want to start taking on the more difficult workloads, high I/O, networking, the bare metal environments, and in particular, get this ready for a production environment so that when we need it, if those curves on run 2 show we do great results from the accelerator, we need to be flexible. Telling people they have to wait 280 days is a very long time. Telling people they can go to the portal, click on the button, and get something in the time for a cup of coffee is the kind of service I want to be offering. So in summary, OpenStack in production at scale at CERN since July 2013. The cultural change for the organization is significant and shouldn't be underestimated as part of this transition. Be it private clouds, be it public clouds, people need to consider the people aspect as well as the technical side. Collaborating with Rackspace has been a very fruitful discussion. We've already been producing results with the open source community, and we have ongoing activities going on for the next year. And in particular, this allows us, as we look at these growth curves coming out towards run 3, run 4, to have a lot of flexibility between on-premise and public cloud resources. So this is a picture from yesterday. One of the first 13 tera-electron volt collisions, the highest ever energy collision observed on the Earth. And we now have 3 more years of pushing back the frontiers of science and finding out what nature has left us as a discovery. Thank you very much.